greetings everybody. So welcome to the next lecture. This is about special topics. We already covered a discussion on vacuum systems. Today we will be talking about plasmas. Although very common all around, in fact, in the universe, as plasma is one of the most common states of matter, but it's not often that we discuss it. But in the context of semiconductor processing, it will be a good idea to know something about plasma, even if not the very deep physics related to it, at least the bare bones and also where it is used. So we will be discussing that today. So today, this particular material I have taken from the introduction chapter of the book by Professor Lieberman and Lichtenberg, a very nice book, a classic book on plasma for semiconductor processing. And I'll just touch upon the things that are relevant to us. First, the disclaimer. This will be the outline of today's discussion. I'll first launch the introduction of plasma, general ideas about plasma, what is plasma and what is it that we use in semiconductor processing, and then give some examples of plasma for semiconductor processing, touch upon some points. Then we will take a peek into basic concepts related to plasma and also the properties of plasma. This is a very deep subject. In fact, it's a subject of research and journals and conferences, but we will just touch upon some of the key parameters that will be useful for you to know when you are in semiconductor processing. And then I'll conclude by highlighting some of the popular sources of plasma. At least one should know the names of the plasma sources, so that when one deals with it, one will not be surprised by what is happening. So what is plasma? Plasma is essentially a mix or a soup of positive and negative charges. So, okay, but overall it is neutral. So if you take a small volume of the material of what is a plasma, and you find out what is the net charge, it is likely to be 0. So that means the positive and negative charges are all distributed all around. But note, in most practical plasmas, that especially those that we will be dealing with, there are likely to be lots of neutral particles also. In fact, in many of the plasmas we use for semiconductor processing, the ionized particles are a small fraction of the total number of particles that are present. Okay, but this is what is a plasma. Well, why does this come about? What is this all about? In fact, it turns out plasma is the fourth state of matter. We know that at very low temperatures, everything becomes a solid, if they tend towards a solid state. If you increase the temperature a little, they become a liquid. And then at room temperature, certain things appear as gases. And if you go to a high enough temperature, everything will vaporize. And if you go to even higher temperatures, if you keep increasing the temperature, it turns out everything will become a plasma. How? The electrons that are surrounding the nucleus, they will be removed because it's at a very high agitation, at a very high temperature, say millions of degrees centigrade. You'll find that the electrons will be shorn off from the atom. And so the nucleus will be positive, electrons are negative. So you'll have a soup of positive and negative, a mix of positive and negative, and that's what is a plasma. And indeed, that's what is supposed to be there in all the sun and the stars, which are at very high temperatures. Now, in the world of plasma and plasma physics, since very high temperatures have to be talked about, it's not uncommon to use a scaled down unit. The unit that they use for temperature is expressed in electron volt. How does that happen? Say a temperature is T Kelvin, the equivalent in electron volt will be Boltzmann constant time T. We have come across this term in terms of the energy that is there. Now, kT, K is essentially 1.38 into 10 to the power minus 23 joules per Kelvin. And if you divide that by electronic charge, 1.6 times 10 to the power minus 19 coulomb, you will get kT in electron volt units. And this is the unit that you use often when you are dealing with plasma temperatures. Let's take examples. 300 Kelvin, which is essentially room temperature, 27 degrees centigrade, As it turns out, as all of you know who would have worked with various electrical problems and of course physics problems and various parts, in fact all aspects of science, it turns out to be 0.026 electron volt. Okay, notice it's much less than 1 electron volt. What's the electron volt value for the surface of the sun, which is around 6000 Kelvin roughly? It is almost half an electron volt. Okay, what is the temperature and at the center core of the sun, which is supposed to be 15 million Kelvin? It turns out using these units, it's 1.3 kilo electron volts. That is 1300 electron volts. Okay, so notice, and at this temperature, everything is in the plasma state in thermal equilibrium. As per the temperature status, what it's supposed to be, it is in plasma state. So at this high temperature, you can see the value is 1.3 kilo electron volt. Now, if you work the other way, what is 1 electron volt temperature equivalent to in the scales that we are used to? It is 11,600 Kelvin. Okay, so notice that when you are dealing with plasma, at least some entity's temperature is likely to be of this order of magnitude, which is why we are using the scale units. I mentioned this because if you go to plasma world, plasma physics, often the temperatures will be in electron volt units, and you shouldn't be surprised what has electron volt got to do with temperature, because they are equivalent by a constant, that is Boltzmann constant expressed in electron volt, or Boltzmann constant expressed in joule per Kelvin divided by the electronic charge. With that background of plasma behind us, let us now look at plasma in the context of semiconductor processing. So remember, in semiconductor processing, we are using non-thermal equilibrium plasma. That means if you create plasma and leave it, the positive and negative charges that are there will end up recombining and it will become neutral. It will no longer remain plasma. So what is happening here? What we do in non-thermal equilibrium plasma is we have ions which are at thermal equilibrium with the ambience. Ions is essentially a molecule which may be ionized, or an atom which is ionized, either of that. And that once it is ionized, the electron is usually shorn off it. So that's one of the ways of ionizing, and it will have a positive charge. And these heavy ions are at room temperature, and the temperature of T ion is, room temperature as you remember is around 26 milli electron volt. The electrons on the other hand, this is the key part, are at very high temperatures, really high temperatures. And how do you do that? You actually pump in energy into the electron in some way. We will see some of the ways in which it could be done later in this talk. And at very high temperatures, and the electrons are more energetic. So the electron temperature would be anywhere from 1 to tens of electron volt. So that means electron temperature can be more than 10,000 Kelvin, right? So it can be quite high. And because these electrons are very high energy, they would be far away from the, that is, they will be moving very rapidly because of the high kinetic energy that they have, and you make use of it in our processing. Usually this is referred to as low pressure, because usually this can be achieved at very low pressures. It can be called cold plasma. Cold plasma because plasmas, as we saw, are supposed to be a thermal equilibrium at very high temperatures. Very high temperatures, everything tends towards plasma state. But this is at room temperature, because the heavy elements that are there, the ions are all at room temperature. So overall the temperature is low, but the electrons, which are very light, are at very high temperatures. Okay, and this is also called often non-equilibrium plasma. Plasma is not something new in a way, because for more than 1.25 century or 1.5 centuries or even more, people have been studying this in the form of glow discharge. You pump down a vacuum tube and then you create a high field to create glow discharge. The glow discharge that you see is essentially a low temperature plasma. So this is what we use in the context of semiconductor processing. Now once you have this non-equilibrium plasma, since there are positive ions and negative electrons, you can use electric and magnetic fields to, if for example, separate out the ions, which is a very useful thing, because ions, once they are separated out, and you can use it for processing for various ways, and then of course it can always be neutralized by any other electron that is there, right? So, and you use magnetic fields usually to confine the ions. You don't want ions and the electrons. You don't want the electrons to move away and somewhere so that they end up recombining. So you want to confine them in a region. So you use magnetic field and electric field, and you can often also use these to extract the ions. Also note, this is something that it's a general comment. Chemical reactions are typically electrons, and that too electrons in the outermost shell of an atom. That's what ends up interacting with another outermost shell electron of another atom, and that's what forms the chemical bond. The chemical bond is essentially an interaction between the outermost shell electron and outermost shell electron of another two atoms. So that means the chemical reactions that can potentially occur, it's not always easy, but it could potentially happen. What is supposed to happen at a very high temperatures, because the electrons, as I mentioned, are at very high temperatures. So they can easily overcome potential barriers and make some reactions happen at a lower temperature, which normally would not be possible. So that is the best part about these plasmas. So you can, for example, plasma enhanced chemical vapor deposition, you end up depositing things at lower temperatures what would typically take slightly higher temperature to do. Why? Because the electrons are at an energetic state. So you can find electrons which are able to overcome some potential barriers which originally prevented the reaction to take place at low temperatures. But at high temperatures, since the electrons will have high energy, they overcome. But here you have taken the electron energy high while the atom energy is not necessarily high. It is at room temperature. So making the electron more energy can make certain reactions possible at lower temperature. This is the best part about plasma processing, one of the features of plasma processing. Then if you look at it, the role of plasma is varied. There are many, and it's certainly not an exhaustive list. I'm just giving a glimpse because we are just trying to motivate the idea that plasma can be used for semiconductor processing. One of the main uses of plasma is a supply of ions. These ions could be atoms ionized or molecules ionized. Okay. For example, O2 plus you could have. Okay. You can also have O2 minus in some situations. You can help reactions take place at lower temperatures, as I mentioned, plasma enhanced processes. So plasma enhanced chemical vapor deposition normally happens at very high temperatures. Because of plasma and the electrons being at a higher temperature, even though the overall temperature is low, but electron temperature being high makes the plasma facilitate a reaction to happen. Besides that, people have used this for sputtering, dry etching, okay, and various ion nitriding, implantation, various places you will find its uses. So actually this is not at all an exhaustive list, not even, these are just examples of what can be done. Now where does the plasma that we use exist? If you look at it, a solid silicon exists somewhere out here, okay. This is room temperature for you. 26 milli-electron volt in log scale would appear to be around 1.5 or so. You can do the calculations and see. So this is what is room temperature, okay. And typically air will have 2.46 times 10 to the power 19 molecules, okay. Now the number of ions that you usually will have at low pressure and low discharge will come somewhere out here. So that means you are operating at much lower concentrations, that is a sparse system, low vacuum, and your electron temperatures are quite high. Notice that they are growing closer to 1 electron volt. Okay, so this is where the plasma that we use for semiconductor processing usually falls. This is a rough rule of thumb. The various other plasmas that one might encounter are also mentioned here. Just for visual appeal, of course, as I said, this is not an exhaustive list. We will be talking about some of these during our course when we talk of unit processing. I just wanted to throw some ideas in front of you. One of the ways plasma has really helped is to extract ions, and these ions can actually help you in reactive ion etching. So you can use the ion to bombard with electric field so that you have an anisotropic, that is not isotropic, anisotropic etching. So look at this particular trench that has been dug. In fact, I would say today they are doing much more than what is shown here, but this gives you a feel for what has been done. This is 4 micron deep. Okay, it's 4 micron deep, whereas the opening is only 0.2 micron, with that is 200 nanometers opening. Today you do go even much smaller, but the point is not that. This is achievable because we are getting plasma to do what is known as dry etching. So plasma, whenever you introduce, often the terminology that you'll find is it's called a dry process, because there's no wet solutions. You have dry processes, and usually you'll find that plasma will be there somewhere, typically. So you use dry etching to be able to dig this deep trench. So you'll say, what's a big deal? First of all, it's very difficult to dig such a deep trench with such an aspect ratio. Remember, it is 4 micron divided by 0.2, so 20 times deeper than the length that you find at the top. Try just digging such a hole on a ground in any field. It's not so easy. Okay, and that too in these small dimensions, you are able to dig this. And secondly, and dig it means you are able to also remove the stuff. So that is a whole game. But remember, these are such trenches often are dug multiple times in large numbers around the same region. Okay, for example, in DRAMs that you build, you have trench capacitors. You may have a lot of these. So the reproducibility, all that is possible because of plasma processing. There is another fascinating process that is there, which is plasma immersion ion implantation. Even for regular ion implantation, you may use plasma to extract ions. Okay, but this is a fascinating process where you immerse the wafer right in the plasma, and then you apply a bias. And when you do that, here a DC bias has been applied. You could use pulse bias also. You'll find that the ions will come and get implanted in the wafer. And this is one of the high throughput methods of doing implantation, because normal implantation, the currents are much lower. But here, because the full region has lots of ions, of course you can control how many ions that are there based on the way you create the plasma. You can have this implantation. It's not just implantation, you could have other processes too. Doping, for example, you can have, and which of course involves a little bit of implantation. Then there are another example. As I said, this is not exhaustive, but I'm just showing some another example here. This is for sputter deposition. This glow that you see is essentially a plasma. Usually it's an argon plasma. Argon because it's an inert gas. You ionize it, electrons at very high temperatures, and the ions can be extracted out with a bias, and they end up sputtering from the target. And once they sputter from the target, the material that is sputtered goes and deposits on the substrate. This is known as sputter deposition, an important process, and this is possible, facilitated certainly by the existence of plasma. And there are many other applications. We will touch upon them as we go through at least one or two more during the course of these lectures. I'm just listed broadly some examples of plasma processing. We already saw reactive ion etching. This is something that allows you to make something anisotropic etch. And actually by tuning it, you can sometimes make it isotropic, sometimes anisotropic, and do lots of tricks in this. So this is a very fascinating area. This is a dry process which is possible because of plasma. Sputter deposition, usually argon is used, sometimes oxygen if it is acceptable to have oxygen. This is one of the ways you can deposit aluminum, tungsten. Tungsten is a very heavy metal, and various films. Films can be made in various ratios, and you can sputter deposit to make sure that you can get that particular ratio on the substrate. Plasma enhanced chemical vapor deposition, which I mentioned a little while ago. Dichlorosilane, ammonia discharges can be used to deposit nitride of silicon. Many, I'm just picking up some samples, and you can also deposit oxides. You can extract BF3. You can also have discharges of CF4, chlorine, and oxygen to selectively etch silicon. This is chemistry, but what you can do is by the help of plasma, you are able to selectively etch silicon wherever it is needed, and wherever you want you can etch silicon dioxide and so on. And this is all dry etching. Another thing that we often do, and this you may even do in your lab, is to use oxygen plasma to burn up the photoresist. Photoresist usually are organic material. You have used photoresist, you have baked it, and now for lithography's purpose is over, you have done whatever patterning you want to remove the photoresist. One of the ways is to use wet processing, to use acetone or whatever in which your molecule dissolves. Another simpler way is you just put it in an oxygen plasma. Oxygen, as I mentioned, it's actually a lot of excited electrons are present, right? So reactions can take place at low temperature. These carbon and hydrogen very quickly burn off, and this is an easy way of removing photoresists and polymers in many situations. Of course, after that you have to do cleaning and you have to remove the damages that may happen and all that. Also, plasma is sometimes used to modify surfaces. If I want to make a film surface hydrophilic, sometimes you may want to bombard it with some oxygen plasma or something, some type of plasma, so that the surface becomes more hydrophilic. Okay, so these are some tricks you can use. We have seen what are the ways in which plasma can be useful in semiconductor processing, at least a glimpse of it. Now let's go deeper into what is this plasma. This is a schematic, your positive and negative ions going all around. One of the ways in which you can do it is using a capacitor with a AC signal, RF signal, and you have a plasma. So these are some of the features of it. These are actually weakly ionized plasma discharge. Weakly means only a small fraction is actually ionized. So if you have 10 to the power 16 molecules at that pressure, only 1 in 1,000 or 1 in a million could be ionized. But that's enough to initiate a lot of the things that you want. Okay. Usually these are electrically driven. Most of the plasmas we deal with are electrically driven, and that means you have to pump in. And why do you need to drive it? Because it's not in thermal equilibrium. If it is in thermal equilibrium, you will have to, you don't have to worry. Once you create the plasma, it will do what it wants. But here, if you don't continuously create plasma, everything will quickly die down. So you have to constantly pump in energy in order to make sure you are able to keep the plasma alive. It consists of charged particles, but remember that there are lots of neutral, we saw that it was weakly ionized, right? So lots of neutral gas molecules are there, and the interaction between the ions and the neutral particles, excited electron and the neutral particles, that has to be brought into the equation to understand what is happening. Because these are not in thermal equilibrium, often the boundary of the chamber in which plasma is created will end up causing a lot of loss. Of course, your goal is to minimize the loss so that you don't have to pump in that much energy through your electrical process. So the losses at the boundary surfaces is an issue. Neutral ionization is what is sustaining the plasma. So one of the primary ways in which plasma is created is the bulk of the neutral ions, molecules that are there, you end up ionizing them, right? So the neutral's ionization is what is sustaining it, and for the process of ionization, you need to give the energy. And of course, electrons are not in thermal equilibrium at all. The ions, on the other hand, are at close to room temperature or at room temperature. So in a way, ions are in thermal equilibrium. in a sense in terms of the temperature that they have. Electrons, on the other hand, are not in thermal equilibrium. That means since the ambient temperature is somewhat lower, they'll be very quickly quenched, and that's precisely the challenge. How do you ensure that they remain excited and you need to pump in the energy? This is just a glimpse. I took this graph from and replotted it from Professor Lieberman-Lichtenberg's thing. This sort of nicely shows what is the electron temperature that you are likely to use. See, plasmas can be of various types, right? Because it depends on the electron temperature and the ion density. These are two primary parameters. Electron temperature, how much more excited is the electron from the room temperature, and the number of ions that are present, right? Number of ions or number of ions is equal to number of electrons, because plasma overall is neutral. So number of ions or number of electrons, you can use one of those things in the quasi-neutral region. So the number of electrons or ions is what it is. So here you see it's very mildly ionized. 10 to the power 8 is all that you need. Plasma ions, plasma electrons, if you want to extract those, if you want some ions for implantation, you could use these. You can extract that and use it for etching purposes and so on. Etch gas, etch products, often you want to make them higher when it is produced at higher density, but notice that these that are produced are at close to room temperature. Plasma ions we know is room temperature, plasma electrons at higher temperatures, and that's what happens. These bombarding ions need not always be in the plasma. For example, if I am doing an ion implantation, I may accelerate the ion to mega electron volt. So that means that particular ion could also be at a much higher temperature at that time, right? So that's also you may want to note. So essentially, the ions are at this temperature, electrons are at this temperatures, and usually the densities are very low. That is a key takeaway from this. Plasmas we use are at low pressures usually, and a small fraction of them are ionized. Ions at room temperature, electrons at higher temperatures. Okay. And if you look at the electron energy distribution, what physics will you use for analyzing them? It turns out, since it's a very sparsely populated environment, you usually pump down to a lower vacuum, and then you ionize it. So the electron in terms of the number of interaction it will have for a given electron's lifetime is actually not so much. So that means you can actually use Boltzmann's distribution. But remember that the energy is high, overall energy of the electron. So somehow you should be able to give electron the energy so that it remains a Boltzmann distribution, but at a higher temperature. And that's what creates all the magic in terms of what you need to do. Here we look at plasma in a chamber. In a plasma chamber, supposing there is a plasma, this is a plasma chamber. Let's have a thought experiment. Initially, supposing all the electron concentration and ion concentrations are equal, and which is true because you are creating something and you cannot, everything is neutral from that, you are creating ions and electrons, right? So the concentrations are, say, uniformly distributed. What is the potential within the chamber with respect to the walls? It will all be same, right? Because initially it will all be same because the electron are equal. So overall potential will be 0 because nowhere is there any charge present. Everything is neutral. If I take a small local volume, number of electrons, number of ions, so potential will be the same everywhere. But it doesn't remain that way. What ends up happening is, if you just wait for some time, the electrons are very energetic, as we saw. So closer to the walls, a large number of electrons end up hitting the walls. Once they hit the walls, they are neutralized. So they end up hitting the wall and they make negative charge here. Similarly, they make negative charge here. The ions are also hitting the wall, but they are just lumbering along because they are much more bulky, right? Thousands of times more bulky. So because of that, what you find is this region is bereft of any electron. Any electron that was there already has reached the walls, and you only have ions here. Now if electrons have reached the walls, obviously walls will be negatively charged, right? They will be at a lower potential. That means any more electrons that are coming which are already negatively charged will be pushed away. This is very similar to the p-n junction theory that you must have studied. So it will be pushed away. So any new electron has to actually have sufficient energy to overcome that potential that is pushing it away. On the other hand, ions will be welcomed. Ions are slow by diffusion if they are supposed to move, but here you have a field that is created and they end up moving. So finally it will equilibrate such that this plasma will have some potential. Equilibrate in the sense, it will maybe I should say finally it will reach a steady state. That is a better word to use. It will reach a steady state such that the electrons and ions that are being produced balance out such that the number of electrons reaching the sheath is equal to the number of ions that are reaching the sheath. Electrons are initially reach the sheath because of their own high energy that they were possessing, whereas ions are starting to reach the sheath. They are going very slowly, but they are accelerated by the field. So these two, when they balance out, you reach a steady state. So the number of electrons and ions that are produced to create the plasma is equal to the number of ions and electrons that are lost to the walls. Okay, so this is how you will end up having if you had plasma in a chamber. So you will find that the region in the center will be plasma, and that becomes actually higher in potential, right? So let's look at the plasma potential and study this a little bit. Electron energy is equal to, this is coming from Boltzmann's relationship, which we all know from gas laws, 8 kT by pi m. But notice that here the temperature is electron temperature, which is much more than room temperature, and me is the mass of the electron. So it's also coming the denominator. So you can see the temperature is high, the mass of the electron is also low, so electron mass velocity is very high. So the flux of electron will be given by this, and initially of course Ne equal to Ni, but in the quasi-neutral region it is also N equal to Ni. So the flux of electron that you will get is QNE, velocity divided by 4. So velocity is given by this average velocity. And ion on the other hand would have similar relationship, but only thing your T ion would be 0.026 millielectron volt, and M ion will be the mass of the ion. Now the question is, at the equilibrium when both are equal, you will want to find out what is the potential that is created. So you can actually work it out that the plasma ends up acquiring a higher potential so that J ion is equal to J electron, and this relationship will be valid at the sheath, at the edge of the sheath. It is similar to the edge of the depletion region. The same physics you will invoke. Of course, the laws of physics are the same. We have Gauss's law, Poisson's equation, and that's what end up governing the whole thing. And drift and diffusion relationship. So at the edge of the sheath, you want J ion is equal to J electron in the sheath. So this is based on that you can write this expression, and usually remember that if you have a P is a plasma potential, but supposing I insert something which is floating inside the plasma, it will acquire a potential which is known as a floating potential, and the floating potential usually is much less than the plasma potential. Using the condition in steady state of ion electron currents being equal, and that ion density leaving the sheath is equal to the plasma ion density, you can work this out, and you will find out that it's nearly, the plasma potential is nearly 10 volts, and this is what is a useful parameter which tells us how much active the plasma is. Okay, so this is one of the parameters you tune in order to do various processing. I would encourage you to look at all these equations and understand the general idea, okay, and maybe work out a few problems. Now, how do you measure it? We saw that the plasma floating potential is what you end up measuring, right? So, there is something called a Langmuir probe. So, there is an electrode that is introduced into the plasma, and a bias is applied to it, okay. Of course, the whole chamber is the other end of the thing, other ground. Now, what you do is you sweep the voltage that you apply to this electrode from minus to plus. And what is interesting is, if I apply a positive bias, what would happen? All the electrons will rush in. That means you will get a current which is equal to the electron current. If I apply a large negative bias, what would happen? You would be able to get the ion current, because electrons are all pushed away because you applied a negative bias. So you will, and only ions are coming, and you will get the ion current, and the ion current will be limited by the number of ions that it can supply, okay. So it will reach steady state. Here electrons will be limited by the number of electrons that it can supply. It turns out that the negative axis interaction will be delta VPF. This is what you are looking for, and this is the parameter that will tell us how much the plasma is ionized, and you can get a lot of other parameters based on the physics that people have worked out. So just like you have a JV curve, or the current density voltage curve measurement for a PN junction and various other things, you can have a similar thing in the case of Langmuir probe, which you use to study a plasma. The Langmuir probe measurement is a very useful measurement for those who want to specialize in plasma. Normally, when you are doing processing, you may not need to do that much of analysis of plasma, but it's important that sometimes you have to collect the parameters that are needed for the plasma. So in that context, knowing the Langmuir probe ideas is a good idea. What are the parameters that people look at in a plasma? There are a range of parameters, and I'm sure they keep increasing as you understand more and more of processing and about plasmas. You want to make sure that the pressure that is of the gas, you can tune it. Typically, in RF type, or the low density plasmas, you have 10 to 1000 millitorr, whereas high density sources, you go to much lower pressures, okay. Then power that you need to put in is 50 to 2000. Notice you at higher pressures, which is relatively to this high density source, you need to pump in more power, right? And of course, here also, I'm sorry, it should be the other way. You are not able to pump in as much power as you are able to do in high density sources. The reason is, whatever power you are pumping in, it should be able to accept it, and that is possible better in the high density sources. The frequency of operation in megahertz is 0.05 to 13.56. 13.56 is an important number, and on the other hand, high density sources, you can have a range of frequencies. Volume depends on the chamber volume, cross section, and magnetic field that you need. Usually you need a magnetic field in high density sources to confine the plasma. And ion densities, notice you get 10 to the power 9 to 10 to the power 11. Here you get 10 to the power 10 to 10 to the power 12. Today sometimes you can even get much higher. Electron temperature is 1 to 5, whereas in high density sources, because you are able to couple the power very well, and also it is very low vacuum, you are able to get them to much higher excited states, and it becomes 2 to 7 electron volts. I would encourage you to check out check out the value for Kelvin equivalent in this. The ion acceleration energy would be 200 to 1000 electron volts. This would be 20 to 500 electron volts. And fractional ionizations is actually very low in this. The fractional ionization will be much higher in this. Although the pressure is low, and because the fractional ionization is more, you are getting higher ion densities here. Whenever you are studying plasma, you'll have to look at all the different reactions that can take place. And this is a study that a lot of physicists carry out. And I'm just giving as an example. Supposing you are using an argon discharge, and I'm sure there are many, many more other reactions they have to look at. So in order to analyze the plasma and how to make it more efficient, what are the main processes that you have to worry about, what are the processes you want to minimize, you need to understand all this. So elastic electron atom collisions is one of the key things that you want to maximize, because you will be able to create ions. Ionization process is this. Then how does ionization take place? Electron type interacting with argon gives ion and excited and another electron. So excitation, the electron will end up giving an excited atom. So this is an electron which is in an excited state. Relaxation, excited state electron slowly will just release the energy in the terms of photon, and then you can have recombination. Electron and argon will end up, argon plus will give you argon. So these are some of the things. So of course you have to make sure you balance the two sides of the equations. So now we broadly saw what plasma is all about. Now let us take a quick look at some of the ways in which you could create the plasma. One of the most popular method of making the plasma is by RF. RF is essentially radio frequency. Radio frequency is the frequency in which the radio signals are usually sent, 3 kilohertz all the way to 300 gigahertz. So somewhere in between, whatever it is, it is often called the radio frequency. Typically one uses 13.56 megahertz, because this is it depends on what frequencies are allowed to be used for processing. You cannot simply come and build something for your processing using some frequency. You'll find the regulators will come in, because it is interfering with the transmission of signals. So people will get upset. So you'll have to work it out. You have to take permissions if something is overlapping with what is prohibited or what is restricted. So you'll have to get those permissions. But typically 13.56 is open for experimentation purposes, for that type of science related purposes. 200 hertz to 40.68 megahertz may also be used, but you'll have to make sure it is appropriate and it's not interfering with any communication thing. So typically you will have a chamber, you'll have a gas coming in. The gas will supply the neutral species, which is supposed to be ionized. If you send in nitrogen, you'll have nitrogen ions with excited electrons. So it's called a nitrogen plasma. If you send in argon, argon plasma, oxygen, oxygen plasma. Each will have its unique features because of the various types of reactions that take place, and you will find that some of them will end up having different colors according to the characteristics of what is happening, the transitions that are taking place. So typically you have two plates driven by an RF source with a blocking capacitor. This allows you to have the plasma potential there. Now as the RF signal goes back and forth, the plasma will move back and forth, and the sheath is on between the substrate and the other electrode. Okay. So now the main interaction is between the plasma used is with the ions and the sheath. That's usually the most common methods by which it is used. You could actually design it such that one electrode is here and the other electrode is a cylinder, circular cylinder. So this way simultaneously you are able to process many devices using plasma. So dry processes, one of the challenges is often the limited throughput that you might end up having. Wet processing, you could have a whole bunch of wafers, you can dip it in a bath, right? So here sometimes that can be a challenge, because the plasma is often not so expansive, right? So you may be constrained, but people have worked around it by building these systems. For example, here simultaneously 6 wafers are being processed with the same plasma that is struck. So these are some innovations that you may also be involved in the future. Now let's see what happens in a RF plasma. Essentially what you do is, RF essentially means it's an AC signal, right? So part of the time this end is positive, part of the time this end is negative. Remember that you have lots of ions here. Overall this and lots of electrons here. Overall, because of the electrons slipping out, this is more positive potential, right? So now when you apply a positive, this whole thing will shift this side. When you apply a negative, this whole thing will shift on the towards the left, and an equivalent thing will happen at the other end. Now if you can tune your RF such that the phase shifts back and forth so that this electron clouds doesn't touch the walls. Without touching the wall, it is going back and forth. And if it is able to do that, you will find some sort of resonance can be created such that you will have ionization increasing and you will have more number of ions formed. So notice that the sheath is usually of positive ions because electrons have all hit the wall, right? So by making sure that you are able to use it, by designing the chamber such that this sheath moves back and forth, and in the process of going back and forth, it is transmitting the kinetic energy, to the electrons and to the atoms to ionize, and the electrons will be excited, right? The electrons will go back and forth. So as they are going back and forth, they will collide, a fraction of them will collide. So if you can just make sure that as it is accelerated, the same frequency at which the electron is ending up colliding. So if you are able to do that, you end up getting a resonance. So the whole thing is about resonance and to tune the whole thing so that you are able to optimize the power transfer from this RF supply to the electrons so that they end up ionizing the gas inside. That's the traditional method, but there are high density plasma sources that have come up. Some of them I am just showing. One of the most popular ones is electron cyclotron resonance. So here what you do is you apply a AC signal in a cyclotron method with a magnetic field. So you have magnetic fields and then you apply a microwave. So these are the magnetic field poles. So there is actually something that is wound around. So you will find that as the signal is coming, the AC signal is coming, electron starts going in circles. Remember that when you accelerate an electron in a magnetic field, it bends, right? So if you are able to make sure it makes a full circle in the same frequency in which you are getting the signal, electrical signal to switch on and off, you will get resonance. So that electron will continuously going in circle. It is very similar to what you will find in a swing. Okay, maybe that will be easier to imagine what is happening. If there is a child sitting in a swing and you push the swing. Now, if you push the swing at a particular frequency, if that frequency is equal to when the swing comes back and is in a position to go back, at that time if you push, energy is given to the system. On the other hand, if the swing has gone forward and somewhere in the middle stage if you come and push it, you are actually dampening some aspects, right? The swing had an ability to had some energy in it to go backward, but here you are pushing it and you are neutralizing that energy, you are dampening it. On the other hand, if the frequency in which the swing is going back and forth is equal to the frequency and in the right phase, that is when the swing goes up, at that point you push the swing. So then you will find that the energy is coupled to the swing. So the same thing here, as the electron is going in circles, you are able to, and the frequency of the electrical signal which is accelerating the electron matches it and is in phase, so that the electron goes in circles, you will end up getting resonance. And that's what is given here. This is the relationship. You are welcome to work this out using basic physics. So 2.45 gigahertz is often when you design it such that the resonance happens at this frequency. Why? 2.45 gigahertz is open for experimentation. You are allowed to do experiments at this frequency because it's kept away from other communications. So you will not be interfering with somebody who is having a radio and they are communicating something. So you design it such that the frequency of the chamber to create plasma happens at this way. just like what we discussed in the RF thing. The frequency in which it is going back and forth, if it is similar to the frequency in which the electron is moving back and forth and in the process ionizing other carriers. So once it reaches very high energy and it collides with any neutral, you have another electron and ion created, right? That electron now starts again oscillating. So you'll keep on multiplying, and of course an equilibrium will be reached when the number of electrons going in is cancelled by the number of electrons that are created, right? So if you balance the loss and the creation, you will get a steady state. So now the ECR plasma is very popular, but you can couple the energy in various ways. Helicon is another method of doing it, where you couple the energy with the RF antenna. You could design it this way, helical resonator, you can use it that way. You can also have inductive coupled plasma. So essentially you use the frequency such that the inductance, there is a resonance that is created so that the electron is able to get the energy, and of course once in a while it will collide, it will create other electron, an ion. That electron also gets into the resonance. That's why you need to go to a low pressure. If you are in a low pressure, you ensure that you don't collide too often. If the collision is too often, then by the time any electron gets accelerated, it collides, you may not get that high an ionization. So it's a very delicate interplay. It's a fascinating field, and I will encourage those who are more inclined towards physics and wanting to do some experimentation to look into this field. Okay, so we conclude now based on what we have discussed. Plasma in equilibrium exists at very high temperatures in nature. Okay, this is it's just something like solid, liquid, gas, and then plasma. We use non-equilibrium plasma for semiconductor processing. A variety of semiconductor processes benefit from plasma. Okay, it's the plasma that is created has energetic electrons which can be used in some ways, has lots of ions which can be used in some ways. And what is interesting is you can create a plasma with almost any gas. So that means you have ions available because you have a plasma process, right? The ions in the plasma are at room temperature while the electrons are very hot indeed. In fact, as we saw, it can be hotter than the surface of the sun, right? There are many parameters that define a plasma, and this is something for those who want to go deeper. Ion density, fractional ionization, plasma potential, these are some of the popular ones you are likely to hear if you are in processing area. And one of the popular methods and effective methods of finding out the properties of the plasma is to use Langmuir probe. If you do a voltage sweep with a probe, floating probe inside the plasma. And that physics, of course, if it is properly designed and worked, you will find that you will be able to get many of these properties that are part of the plasma system. RF plasmas are quite popular, but the fractional ionizations are usually lower. You operate at a slightly higher pressure and you get some ionization and some number of ions. Higher ionization plasmas usually operate at a lower pressure. You have higher ionization fraction, and overall you find more ions being created. So this is just a summary about plasma, and I am sure we will be mentioning about it. And if you are going to be working in the field where plasma is used, it will be good for you to learn more about this. There are many books out there, lots of excellent physicists working in it, including at IIT Kanpur. But this is one of the popular books, in fact, Lieberman and Lichtenberg, which dwells into the physics of it, especially in the context of semiconductor processing. Thank you.